Assalamu alaikum and good day everyone. My name is Mustafa Mahmoud and today I'll be doing a demonstration video regarding my final year project thesis called named MIMO Wideband Antenna for 5G usage. The MCMC in Malaysia has announced that for service providers and companies intended on using 5G communications will have to adhere to certain frequencies to use in 5G. These frequencies are the 700 megahertz band, 3.5 gigahertz band, and 26 gigahertz band. So for this design, we will be focusing on 700 megahertz and 3.5 gigahertz bands. Previously, during the first phase of my final year project, I had designed a single port antenna, which I am showing right now. It is composed of a rectangular patch with the 10-step cut at each corner in order for the patch to operate on multiple frequencies. The patch is supported by a transmission line with no inset feed, and it is supported by a partial ground. The substrate used is FR4 and it is square shaped. The design covered the as we can see from the return loss parameters, the design covered the 700 megahertz band, but did not cover the 3.5 gigahertz band. And it also did not achieve the gain, the required gain specified in the requirement specifications. Hence, the next step would be to design a multiple port or MIMO design based on this design. So we're going to basically utilize this design to create a 4-port MIMO design. As we can see here, our 4-port MIMO design was created by joining 4 patches of the same size from the previous single port design. After some altercations by deleting common areas between the patches, this was the final shape of the patch. Each patch or each side of the substrate is connected to a feed line, and each feed line is supported by a ground. Typically, each feed line is supported by a partial ground, as I did in the single port design before. But after compiling the return loss results, it was found that the coupling effect between the ports lowered the efficiency and affected the energy distribution of the antenna. Thus, the antenna couldn't operate on the required frequencies. To counteract this increase in coupling, I added a parasitic element to the ground. This small rectangle above the ground is called a parasitic element. We call it an L-shaped slot since at each corner is shaped like an L. So for this parasitic element, its width is about a third of the total width of the partial ground, and its length for this trial we used an 18 millimeter, which is the same length as the ground or as the partial ground. We later on explore the difference between the sizes of parasitic elements and its effect on the S parameters. After checking the S parameters on this design from port 1, port 2, port 3, and port 4, we can find that the frequency 700 megahertz and 3.5 gig band were not achieved, although its isolation parameters we can see here for isolation parameters from port 1, port 2, port 1 to port 3, and port 1 to port 4 were all less than negative 10 dB, which is a very optimal level of isolation. Thus, we started to improve the patch by increasing the number of steps. Increasing the number of steps at the corner usually means that an infinite number of steps is a straight line. So we utilized this design that we are seeing right now, straight lines. We also tried different sizes of parasitic elements. This design is 10 millimeter length. We tried to alternate the width, but I noticed that there is no difference when we change the width size of the parasitic elements. No difference or very little difference is noticed in the S parameters. So we will only be changing the length of the parasitic element. So we used 10 millimeters, 18 millimeters, and 27 millimeters. I compared between them, and I found out that 18 millimeters was the best or most optimal length for the parasitic element, which made the best isolation, which resulted in best isolation, and almost the best S parameter compared to the rest of the S parameters we looked at. So here we can see that what we noticed here is that the the design needs to shift its operating frequency. So when I was studying for theory, I noticed that we can shift the operating frequency of the design by lowering or making the design patch more smaller. So when we make the patch smaller, the operating frequency seems to tend to shift to the right a little bit, which is what we want. So this is what I came up with. I scaled the design and reduced it 10% smaller than the original single input, single output design, and I also added infinite number of stepped corner. For this reduced design, I used two variations to compare. One is with a ground, partial ground, and parasitic element of 18 millimeter. The second one is supported by a full ground. As we can see here in the design, it is supported by a full ground. We will compare between them now. So for the for the partial ground parasitic element, we can see that the the target band is still not achieved, and we check isolation. The isolation is still less than negative 10 dB, which is very optimal. When we compare it to the full ground, we can see here that full ground return loss can achieve what we have. So starting off with the return loss, the antenna seems to operate from a minimum of 0.69, therefore 0.69 megahertz, therefore covering the 700 megahertz band, and operates at 3.4 gigahertz and 3.6 gigahertz, therefore also achieving the 3.5 band. And it is also noticeable to say that it also covers 2 gigahertz band, which is the UMTS band, although it is not a requirement in the specification, but it can be taken as an advantage to this antenna. Next up, we see the isolation. We see the isolation parameters. So by taking normal random values within the 700 megahertz and 3.5 gigahertz band, it is seen that the isolation is greater than negative 10 dB for all ports except the one between port 2, except isolation between port 2 port 4. We can see here that it is quite higher than the rest of them, port 2 and port 4. So for further research will be done in the future to enhance this. Following this is the envelope correlation coefficient. It is noted that at the same random values, it can account to lower than 0.2, and also the diversity gain range from 9 to 10 dB, which are acceptable values. Now, here the diversity gain that I was talking about. So for 3.5, it's about 9 dB, and for 0.72, it's about 10 dB. These are acceptable values for diversity gain. And for the ECC, 0.1 and 0.005 is also acceptable. So for the gain of the antenna, we can see that for the same random values, 0.72 and 3.5, the gain ranges from 5 dBi to 6.6 or 6.8 dBi, which matches our specifications that we set before. To calculate the antenna efficiency, we needed to simulate the diversity gain. So antenna efficiency is basically gain over directivity. I mean, sorry. The efficiency is basically gain over directivity. So to calculate the efficiency, we simulated the directivity. Here you can see the directivity values. So for the 720 megahertz or 0.72, the efficiency will be, after we calculate it, it will be 80%, and for 3.5 gigahertz will be 70%. The target efficiency for the design is over 50%. So I think 70% and 80% we already achieve the target efficiency for our design. Concluding, the simulated results for the MIMO design can operate within the 700 megahertz band and 3.5 gigahertz band and can be used for the project's purpose. As a next step, fabrication process will be done to test the antenna on a real-life system. Now I will explain briefly how the fabrication process will occur. So first we will go to modeling and we will export a DXF file. So we need to select the patch layer first. We need to first select the patch layer and export a DXF file. After that, we can save the file, but whatever name we want. Then we open any drawing application used on PCs to color the patch so we can differentiate it from the substrate material. We color the patch black so we can substrate it when printing the material. Also, we scale the patch to its original parameters. Then we use an FR4 substrate sheet and cut it into our desired dimensions. Here is a sample of the process of application that I did with during my final year project 1. So first we use an FR4 substrate. Here we can see the FR4 substrate and cut it into our desired dimensions. For our project, it's about 169 millimeters, the width and length, because it's a square patch. Then we print our design on a paper. It's a special kind of paper that can be found in most electronic stores. After that, we stake the paper on the substrate sheet, and we use the PCB heating machine to transfer the design onto the substrate board. After the design is fully transferred on the substrate board, we use a marker to do some spotting to fill out any empty spaces in the batch that are caused by losses during the transfer. Then the chemical cleaning process is used so we can expose the substrate material. After that, the antenna, the connector is soldered to the antenna using a solder gun, and it is ready to be tested. So we can supply the power to the antenna using the connector, and it is ready to be tested in any project or a chamber in the lab. This will be all for my demonstration today. I hope I hope that I reached my point and that I was clear and can be understood. Thank you for listening. Have a nice day.